Welcome again with us. Today is the eighth session. It will be conducted by Rich. Um, Welcome, Rich, to
Thank you
Omdena
so much.
Algeria chapter. We would really thank you very much for accepting to deliver us this workshop and to join us. Thank you very much, and please go ahead.
Thank you. It's a pleasure to be here. Thanks for having me. So what I want to show you today is an example of an end-to-end project using both a manual investigation and model building technique and also H20 auto machine learning, which is a library which basically automates the whole process. And they seem to be being used more and more in industry, in my experience. So I think it's a key piece of knowledge to take away. It's not going to replace machine learning engineers or data scientists, but it just helps automating certain parts of the process. So it is quite an interesting subject. Now, the data set I've picked today to show you, to give you the example, is a drinking water potability data set. It contains 326 different lines in it, and all of them are single samples of different water bodies. Drinking water, access to clean drinking water is very important in a lot of developing countries. So, you know, projects like this really do make an impact. However, what my sort of angle is on this one, this data set has been artificially generated. And to be honest, the data isn't that great, because what I want to demonstrate to you is that in industry, it's very, very rare, if impossible, to get a nice, clean data set which you can automatically plug in to your machine learning model and get a worthwhile result. And I think machine learning tutorials and courses online don't really show beginners that when you work in industry, the chances of you finding a nice data set which needs minimal sort of investigation are very rare. So I want to show you a poor data set, and I want to show you how to ask the right questions about the data set. What does it mean? And that way, if you understand your data very thoroughly, you can make amendments to improve your model. And I don't think them sort of lessons are captured in beginner machine learning engineering courses. So first of all, we'll go over the project steps. We're going to import the libraries and the data set. We're going to take a quick look at, you're going to do some data analysis and pre-processing. We're going to then ask a couple of questions around the feature engineering. We're going to manually build a model, and then we're going to build a model and prediction using the automatic H20 AutoML. So the first step we do is import our libraries. Now, the libraries that we are going to use today, they're going to be NumPy, which is for your mathematical calculations. We've got Pandas, which is, I would describe it as like Excel within Python. It allows you to make data frames which are very similar to databases, and you can, chop up and manipulate the data from there. Matplotlib and Seaborn, they're both visualization platforms, which are very useful for data analysis and understanding visually what your data is about. So first of all, I've uploaded the data into the Google Colab, as you can see here in a CSV format, and we load the data set using the Pandas read CSV. So we load that in, and we'll check the head by using dataframe.head. So this, it gives us the first sort of 5 rows of our data set with a 0 index. And as you can see, we've got pH, hardness, solids, chloramine, sulfates, conductivity, organic carbon, and so on and so forth. The potability is whether the water has been deemed safe to drink, and that is with a 0 for no it isn't, and a 1 for yes it is. So the next sort of step to understand the dimensions of our data is using the Pandas method shape. If you take a look at that, and we've got 10 columns, and as I mentioned before, 3,276 observations, and each one of them is a single sample taken from a individual body of water. The next step, we take a look at the info. Now, what the info does is basically show you what kind of data is contained within the data frame. So as you can see, the pH, all of them are float 64s, apart from the potability, which is binary. And as you can see here, we can notice that not all of the entries in a couple of the sections seem to have the full amount of observations. So that means they are NaN values. They don't exist. So we will have to deal with that. So then we can go to and check the number of unique. Again, we can see that there are some that aren't matching the full data set. And of course, we've got the binary outcome of the potability, the 0 and the 1. So let's explore the data a little. The describe function is a very important one. We can get an idea of sort of statistical figures about our data, so we can get the mean, standard deviation, the minimum value, the 25th, 50th, and 75th percentile, and the max value within that within that observations range. And as we can see, a couple of observations here. So the mean of pH is 7, and yeah, you would, that's neutral. So you would expect that to be that, but then the max value in the pH is 14. So that is massively alkaline. So which I would say would be very unusual to find that in a body of water. So that is quite an interesting observation. And of course, there's other values that you can see here. The 25th percentile is 6 and whatnot. It does make sense on the initial look. So we'll take a look at the target column and see what the distribution is like. So as you can see here, we've got a number of more zeros than we have ones. So a lot of the data within the data set is it leads to the water not being drinkable. I wouldn't say this was particularly unbalanced. It is slightly, but I don't think it would be a massive cause of concern at the moment. I mean, if the one was sub 250 observations, then we would have a severely imbalanced data set, and we would have to try and improve that using techniques like oversampling, or using different sort of metrics to analyze our model performance. But we'll get into that a little bit later on. So we know that there are a couple, using the describe functions, we know that there are definitely some null values. So let's check where they are. And there we use df is null sum, and what we can see here is basically a sum of columns, a count of the NaN values on the data set, and you can see 491 in pH, sulfate 781, and trihalomethanes, I think that's the way it's pronounced, is 162. So we can take another look at that. It might be easier to sort of visualize. We can see calculate using this formula here. I calculate the percentage of missing values. Now our data set is only small, so we can't. I wouldn't really recommend removing any of these missing values. Say if we had a data set of 100,000 observations, I would be happy removing them completely out of the data set. I wouldn't be happy moving these because that is quite a significant portion. But anything below 5% in a massive data set of around 100,000 observations, you should be fine to remove them. But in this case, we're going to take a look at the distribution of these 3 columns, and we're going to see what the best way of imputing these values are. So if we extract the null columns, we can see these are the ones that contain the null. We can visualize the null column, the null value observations, and we can see how it looks. And it, some of them, it seems that it doesn't seem to the align up. So It's not as, are these just errors? Was this data not collected properly? Did the sensors work? Was the sampling off or anything? There's no indication of that, but it doesn't seem that these seem to be, there's no consistency between the three entries. So that's quite handy to know. So let's have a look at the distributions of these columns. These are the distributions. So you can see that all of them seem to be quite, Gaussian, normalized, quite a normal distribution. So that gives us an idea of what we can do to impute these missing values. So let's just drill down a little bit. So we'll take a look at the pH first. And as you can see, yep, it's got a normal distribution of values within there. So that would say to me, I would be more than happy to replace these values with the mean or with the median. In this case, I'm going to replace them with the mean using NumPy. The sulfates, again, the same story. Got a normal distribution. I'd be happy to use the median or the mean, and I'll use the mean in this case. And then we have the trihallomethanes, which are also slightly different, but generally normal distribution. So again, let's hit it with the mean. And then what we can do is check if that's done correctly. And as you can see, there's no more missing values within our data set. So that's fine. Now, another sort of data analysis that's quite useful is a pair plot. And what a pair plot, I ran this earlier on just because it takes, maybe up to 5 minutes to run. I didn't want to waste anyone's time hanging around. So I ran it earlier on. But as you can see, this, as I mentioned earlier on, this was a synthetically generated data set. And just taking a quick look at, the distributions, there doesn't seem to be any sort of coherent relationship between the features within our data set. So there doesn't seem to be any correlations whatsoever. And that is quite interesting because you would expect certain features to align with the outcomes, whether the water is drinkable or not. So let's take a closer look at that. We'll take a look at the outliers. Now, outliers are basically anything that fall in a sort of terms of a box and whisker plot. Anything that falls outside of the 25th, the whiskers here, is deemed as outliers. Now, outliers are very domain specific. So an outlier that you see in the data set, if you know your domain well enough, you will be able to say with some degree of certainty whether a value is actually an outlier or not. This is a water data set with samples of water, bodies of water, to test whether or not it's drinkable. So we have outliers on the pH, and some of the outliers lie at 0 and 14. Now that is really acidic. It's the top of the scale for alkali. So what is this an error? Are these mistakes to it, especially with a 0? Was the data captured at all and it's just been translated as a 0, or was the water actually that acidic, which I find quite hard to believe. But as you can see, so they will be outliers which I think need more investigation. And it's the same with the sort of hardness. If the pH is that, what's going on with the sort of, these are the sorts of things that you'd have to investigate if you're in the domain. It'd make a lot more sense if you were in the domain, but as we're not, we need to look at it a little bit more harder, do some background research about what is expected. And this is what I've done. So we'll ignore the rest of them, but we'll take a look at the pH because I think that was the easiest one to understand. So the pH is many outliers, and we can explore that. And I found that EPA's recommendation for safe drinking water, the pH has to be between 6.5 and 8.5. So let's pull all the entries with the pH higher than 10 and lower than 6.5. So we take a look at the ones that say the possibility is 1, and this is saying that the pH is over 10. Now, the recommendation is 8.5. So we have values 8s all the way up to 13, 14s. So why the pH is so high? Has this water been marked as safe to drink? They're the kind of questions you need to ask. So let's take a look at the bottom end of the scale. We've got the acids below 6.5s. We've got 6. We've got 3s, and that is like really acidic. And again, they've been marked as 1. This data set is synthetically generated. It's not a great data set. A lot of the features aren't correlated. But what I'm trying to show you is you need to, in industry, you do get data sets that are absolutely awful, and you need to explore them and ask these kind of questions. Why is our water being stated as drinkable when the pH is acid? They're the kind of questions we need to understand. So I've wrote here, it is curious that some of the entries for potability are 1 while the pH exceeds this range. Bleach has a pH of 12, and we do have some entries in there which are higher than 12, which state that it is drinkable. So how would we deal with this? We'd have to research into why these values have, if you were in industry, someone has collected this from your place of work, and you would have to contact them and say, why is this information as it is? Why is this water being classified as drinkable when it, the pH is off the charts? Are the errors? Are pHs relaxed when the pH sort of the safe drinking scale? Are they relaxed when water is in desperate need? Maybe, but would it be relaxed to 14 and 0? Probably not, because it would it cause someone severe harm. So what I'm going to share this project, and I think for practice, I think a good idea was to go away, use this information and research about water, and see if you can make amendments to this data that makes it a bit more coherent with what we would expect. I've linked to a couple of scientific publications on potable water and how it is analysed and how it is classed. So taking that into account, for now, we won't go much more into that. I'd like you to go away and take a look at that into yourself, just for a bit of practice in how to understand your data set and what you need to do to make sense of it and how you would adjust it. What we'll check is the correlations, and we will use the correlation function of pandas, and it gives us this table of the correlations. And if you're like me, I'm a bit more visual. I don't like looking at a lot of numbers on the screen. So what we can do is plot this, and it makes it a lot more easier into a heat map. And here we have a heat map. So what is quite interesting is that there doesn't seem to be much correlation between features. Synthetically generated data set, there isn't going to be much correlation. So what that says to me is that our model is going to struggle to make a good prediction, because the features that we have in our data set aren't really given much information to the target, basically. So it's not telling a story which will make the target either 1 or 0. And what we would do in that case, if this wasn't a synthetically created data, we'd do some feature engineering. So what we mean by feature engineering is that we would either create new features by combining 1 or more features. We would, if we were able to find more information about how this data is collected, we would add it to our data set and make it a feature. So there's a number of different ways to do that. And what I want you to do, if you do have the time, take a look at water data sets and see if there's anything that you can pull in, or if there's anything that you can change or combine within this data set to allow the features to tell a bit more of a story. What we can do as well, feature engineering, a big point in this is that we can check the feature importance. And what that means is we can see what features are important for our to make a prediction, and what is important for our target value. And we can do this by using scikit-learn. And in this example, there's a number of different models you can use to do this, but in this particular instance, I'm going to use the extra trees classifier. So what we do is split the data into X, which will be all the data other than the target, which is the potability binary class, and Y, would be the target class. And we fit the extra tree classifier to that data, and we can print the feature importance. Again, it's a series of numbers. Let's take a look at it visually. And what we can see here is that all the features are actually quite, according to the extra tree classifier, to make a sort of any sort of sense of the target, it seems that, you know, the features in the data set all are quite equal. Now, if these, like, say, if turbidity and conductivity were really low, I would suggest that we could drop them features, because they're not really telling us much about the target. They're not really telling much of a story. So we could drop them, but it seems that, you know, according to the extra trees classifier, they're all quite equally, you know, not far off equally important. So we can keep them all. The next step would be to split the data for the model developments. We've done a bit of data analysis. There's a lot of things that we could change here, but I want you to go away and have a think about it. And also, we could sit and look at that data all day, and obviously we don't have the time. So let's split the data for model development. And it's important that we do split the data for model development before we do any sort of transforming of the data. If we don't, we can have data leaks, which basically means your model is able to cheat. It'll already understand what makes a good prediction, and we don't want it to do that. We want to teach it how to do that, not show it how to do that. And there's a big difference. So the standardization and scaling of the data, what we're basically going to do is bring all the values into a similar range. This makes it much more digestible for a model, for a machine learning model. So let's take a look at the head again. As you can see, the numbers are are quite all over the place. And what a machine learning model will tend to do is place higher importance on a larger value. So what I'm going to use here is the min-max scaler, and that will scale our values into between 0 and 1. So if I fit and transform our training data, and we only do that on the training data, a fit transform on the training data, we can add them scaled them values to another data frame, and as you can see, it's brought them all into the same sort of scale, which will be perfect for our model. The next step would be then to transform the test set. However, we do not fit it to the test set, because that would then cause a data leak. We only need to transform, so we're only transforming it using the calculations. It's not using the calculations applied to the training data. We use them same calculations on the test data, which means that's why we only use the transform function. We don't use the fit transform. So if we do that and take a look, we've got our test set, our X test set, and there we go. It's scaled it using the same formulas, but it hasn't leaked any data whatsoever. After we've done our transformations, we can then go on to start building the model. The model I'm going to use is the logistic regression, because it's a binary classification task. Support vector machines, and that works by finding decision boundaries and hyperplanes in high dimensional spaces between the data. And I've created a YouTube video just to talk about that and how it does that, if you want to take a look at that at a later date. A random forest is an ensemble learning technique which combines a number of single decision trees and uses a bagging method to determine the prediction or classification. And XGBoost, extreme gradient boosting, is a scalable gradient boosted decision tree, and it puts all the trees in parallel, but what it means by gradient boosting is that it uses the results of the previous tree to start off the next tree. So it gets stronger and stronger. It makes the lower values much stronger, and you usually get a very good prediction. XGBoost is the king of tabular data problems, and we're going to use a couple of different metrics, which I don't think we have time to go through every single one of them, but I've provided information about confusion matrix, F1 precision and recall, and the Rock Oak score as well, and how to interpret them when you're building a machine learning model. We've got a minute left on this. Should we refresh and rejoin?
Yes.
Yeah,
we
cool.
should reconnect if you permit. Yeah. So please,
cool.
we will refresh and then reconnect. So please be there, okay?
Cool. Okay, welcome back.
Yes,
Everyone see me?
so please go ahead. Yeah.
Cool.
Thank you.
Okay. So the first one we're going to take a look at, we import the libraries from scikit-learn, and from XGBoost library, we import the XGB classifier, and we import a couple of metrics: accuracy score, confusion matrix, and the classification report. So if we run that, they are all brought into our workspace. The first one we'll do is the logistic regression. So I import an instance of logistic regression, I fit it to the training data, and then I use it to predict on the test set, and I build a classification report, a rock out score, and the confusion matrix, and then a measure of the accuracy. So let me just run that. And these, the print, just to make it a nice simple layout. So what we've done here is run that, and the results, you know, aren't that surprising. The model hasn't performed well at all. Take a look at the rock out score, that's 0.5. That basically means the model isn't doing better than a flip of a coin at this point. And that would generally be down to that the correlations in our data that we observed earlier on in the heat map isn't giving the model much to go on. So it's basically randomly assigning 0 or 1, and that isn't great. It's not reliable. And as you can see, the F1 score, which is a metric, which is the sort of, I wouldn't say average, but it's the harmonic mean of the precision and recall. The closer to 1 the F1 score is, the better your model. In this case, you can see that the weighted average is 0.46, so it's not great. But again, as we can say, it's a flip of a coin at this point. The test accuracy score is 61, but I wouldn't really rely on that, simply because the information, we can say that the model isn't using the data set correctly, and it's just randomly applying that, so that isn't reliable. Accuracy score in classification problems aren't the greatest, especially if you have a imbalanced data set. So for the time being, probably the most important, in my opinion, I mean, this does change depending on what sort of problem you're tackling, but F1 score is probably one of the best metrics to get for a classification model. It is probably the most reliable for most of the situations you come across. Your imbalanced data sets, though, precision and recall can be more weighted towards them depending on the situation. Okay, the next one we're going to look at is the support vector machine. And the layout is exactly the same as the logistic regression, except the only difference is that I import an instance of the support vector machine. We'll take a look at that one. And again, it's very poor. It seems to be having the same trouble as the logistic regression. It's not being able to adequately create the decision boundaries between the two target values, 0 and 1, based on the information contained within the data set. Again, 0.5 rock score. That basically means it's not doing better than a flip of a coin. And as you can see here, it's getting 600 true positives in the small confusion matrix, and it's getting, it's not. If it was doing 100% well, these values here would appear here. It's not. It's classifying it. It's either that one or that one randomly. It's not making any sort of decision whatsoever, which is not surprising, really. The random forest, we'll do it again. Exactly the same, but I import a random forest classifier. And we'll take a look at that one. Now, this seems to be doing a little bit better. It's digesting the information contained within the data set a little bit better. As you can see, we've nearly got 0.6 in terms of the Rocco score. And that basically means that it's better than the flip of a coin, but it's not that much better. The accuracy on the test data set is 65%, and on the train data accuracy score, it's 100%, which is quite unusual. Too good to be true in most cases. But as you can see, the weighted average of the F1 score, 0.62, is significantly better than the previous two models. So, you know, it seems that a decision tree model is probably best suited for this kind of data set. So let's take a run on the XGB classifier. It performs slightly less than the random forest. And as you can see by the metrics in the confusion matrix, it seems to be classifying a little bit less as well. But it gives a more realistic sort of accuracy on the train data and the test data. So I think the gradient boosting tree, despite it running a little bit less than the random forest in terms of accuracy and rock out score, it's probably the one to take forward. It seems to be a bit more interpretable. Now, we can alter these. I only run them without sort of defining any sort of parameters or hyperparameter tuning. And what we can do for each one of them models, if we use the get params method, we can get the parameters that the model used to make these predictions. And what we can do is use these to test. We can change the values in them, and we can try and push out more performance from our models. So we could increase, for the tree-based ones, we could increase the max depth, we could increase the max leaf nodes, and all that would have a effect on the performance. Now, it doesn't mean if you modify these numbers that you're going to get better performance. You could get worse. The trick is to try and find the best combination of these hyperparameters, and it can be done manually. It takes a long time, but it can be done automatically as well. And there are packages such as Optuna, which basically find the optimum hyperparameters itself out of the full array. What I'm going to show you is this here. So I've taken the XGB classifier, and what I have constructed here is a parameter grid. So I've taken a look at all the possible parameters that XGB Boost uses, and I've basically made a dictionary of different parameters. So you can see the N estimators, how many trees are contained within the model: 100, 200, 300, 400, 500. The minimum child weight, 4, 5. The learning rate, I've used various different numbers. The gamma, I've basically looped through it in steps of 6, and I've done a similar thing with a number of different parameters in there. And then what I've done is use the randomized search package. And what randomized search will do will basically run through all these parameters at random, and it'll cross-validate them. And what it will do is spit out the optimum hyperparameters to get the best performance out of these particular settings. It does take a while to run, even with a GPU. It's been run on a GPU, and it did take about half an hour to run, but I've already run it just so you can see the output. And according to the parameters I put in there and the randomized search, the optimum parameters are these ones here, and we can then plug them into the next run of the model. Now, the good thing is we don't have to type them all into this space here. We can use the best model, best parameters method here, and that will export them into our next sort of iteration of the model. The random state is set at 42, just to make, if you run it yourself, you'll get the same results as me. And the tree method again is that we need to use a GPU to get the best out of the model. So if we run that one, it'll take a few minutes, and as you can see, it's improved our rock out score to 61. It's improved the weighted average at the F1 score, and it seems to be doing a bit better in the confusion matrix in terms of its classification of true positives and true negatives and whatnot. And the test data accuracy has improved a little bit as well. It's still not great. if we were to put this into production and it said the water was drinkable, I probably wouldn't drink it. And that's because I know what the data is saying, and I know that the data is I included it to purposely be tricky, just so I could show you the sort of thought process around analyzing data and what the kind of questions you need to ask when you're in a machine learning pipeline. So the next step is the voting classifier. Now, we know, and what the voting classifier does is it's basically it trains the various base models and predicts on the basis of aggregating all the findings of each base estimator, and it votes on the best outputs. And we know the best performer models with the random forest and the hyperparameter tuned XGB boost classifier. Sorry, so we can run that, and what it basically we're doing is stacking them together. So we're inputting a list basically of tuples into our voting classifier instance, and then we fit it to the train data, and then that gives us the sort of the hyperparameters. What we've fitted, we can see that the random forest classifier is run on the random state of 1, 2, 3, and these are all the optimum parameters as chosen by our randomized search. So let's see what the performance is. We take a look, and to be surprised, it's actually gone a bit lower, which is quite surprising. It seems that our XGB classifier was better alone, and there could be a number of reasons for that. The results could be cancelling each other out. It could be the data set. We know the data set isn't great, so it's just struggling to make sense of it, especially when it's being combined with another model. Another way, I haven't done it here, but another way is stacking them. So you could stack models together that use different methods to cancel out the negative. So we could stack a logistic regression model with a random forest model and see how that works. Hopefully the strengths and weaknesses would play on each other, and we could get a better performance. That is an option that we could try. I just haven't done it in this instance. So that's what the best result we got was 61 with a weighted average of 64. Not great, but let's just see what we can do with the AutoML. Now, the H20 AutoML is a very easy to use package. The documentation is absolutely fantastic, and I've also included the evaluation metrics, the detail about it, because it uses a very broad amount of evaluation metrics. It uses the same ones that we've used, but there's so many users that I possibly haven't got the time to cover it all. So I've left the documentation there so you can take a look in your own time. And also I've included the parameter appendix as well, just so you can see exactly what you can do to hyperparameterize the model. It's already installed. I've already run these because it does take a bit of time to install into me Google Colab instance. And I've also checked that there's one instance of it running. I've imported the H20 and imported the AutoML part of that as well. I've loaded the data set, and it's been passed 100%. I've taken a look at the head, and this is the raw data set. There's been no amendments to it. So we can take, there's still the missing values in there and whatnot. We can also use a very similar describe function, but it gives us a lot more in-depth information about our data set. And it gives us a real understanding of what's in there. This is the same sort of table as the pandas describe function. So as you can see, it gives us various different metrics: the min, the mean, the sigmas, and whatnot. So the advantage of AutoML is that it cleans the data for you. So first of all, what we have to do is change the target variable to a categorical variable, and it's a little bit different to pandas. I've already done that, sorry, so that's why that's not working. Just clear that. But you change it to as factor, and as factor means it changes it to a categorical variable. So it's a binary variable, 0 and 1. And what the output of the H20 will be is that it gives us the probability of what the true prediction should be, which you will see. So when we split our data into a split frame in AutoML, it'll automatically do all the data pre-processing. So it'll fill in, it'll scale the data, and it'll also fill in any missing values at all. So we can run that one. Why is it data split frame? Is that because bear with me 1 second, let me just rerun that one. I might have to just re-input the data because it might have timed out. Yeah, there we go, that's the reason why. So it split the data, it's filled in all the missing values, and it's scaled the data. So what we do with this at this point is we build a model. The max runtime is 500 seconds. The max model is 25, so it'll run for 500 seconds. You can set that to whatever you want. The max models, it'll pick between 25 models, and it'll put them all together and train 25 models to give us the best results. The balance classes is set to true. So what that is basically similar to Stratify, it'll train the models, and it'll give a balanced look at the probability. So it'll remove the imbalance between the classes, and it'll cross-validation n-folds there. So if we run that one, it's the model's fitted, that's fine. We define the training, we define the target as possibility, and the X as the columns, the features within our data set. So we set that. So I've already trained it, and it trained it on 25 models for 500 seconds, and it gives you then all the metrics of each of these models. So there is the training, and obviously some of these haven't trained fully, only because they need more time. We didn't have the time to do that, so this is why I had to speed it up, hurry it along a little bit, and it'll give you the various different metrics of all the models, and we can go through every single model, and it gives us all the metrics of them: the accuracy, the out score, the error count, the F1s, the F2s. It gives us every metric we could possibly desire, but we only want to take a look at the leaderboard. So it does have the leaderboard function, and if we run that, oh, it has to be trained again. Give me 1 second, I'll just have to let that train. So let's just let that train for a couple of minutes. Is there any questions so far about what you've seen? This is also the problem with H20. Sometimes if you reinstate it, it forgets all what you've done so far. So as you can see, it's running through a number of different models, and it's using XGBoost as well, and it uses deep learning models. It just tries to find the best model for your particular data set, and it'll run it all against each other, and it is quite effective at doing it, and it gives us a full metric breakdown. We'll just give it a couple of seconds and see what it does. And as you can see in the output here, it's got the hyperparameter search. So it's actually searching for hyperparameters automatically as well, which is very handy. These hyperparameters can be used, you can edit them manually, but if the AutoML does it, I don't think there's much need to do it yourself, unless you have a specific target that you want to get to. And I'll just run these ones as well, because it'll all spit out. So yeah, is there any questions so far, or any comments, or is there anything that you didn't really understand, or you'd like me to explain a little bit more in depth?
I have one question, if I can. So if we have a data set with no obvious correlations between features, just like this one, you said the main strategy is to do some feature engineering. Mm-hmm. But what if that doesn't work? Is there anything else that we could look into, like we could try?
Yeah, so depending on what, so in our sort of context, we want to basically find out whether water is drinkable or not. So we would understand the data set that we have. There's a couple of elements in there that are completely invalid. We know that we can't drink water that's 14 pH. So what we could do again is synthetically create data which is in the values that we would expect safe water to be in. And what we could do is train a model on that synthetic data, which would be able to recognize the differences between drinkable water and not drinkable water. If we set them parameters to say the pH has to be between 6.5 and 8.5, that means the water is safe to drink. And we could do that for each section, the hardness, the chemical content in that water. If we were to train a model on the expected values, we could then apply it to this data set. And we could see that, you know, the values outside our expected values wouldn't be safe for drinking. That's how we could do that. We could artificially create data. In industry, we could, one, artificially create data. If you received a data set like this and you were asked to build a model to detect drinkable water, and you received the data set this bad, we could probably go back to the source and we'd have to, you know, reevaluate the data. Someone would have to collect it again because it's not great. If you were unable to make sense of it by feature engineering, adding more data, or enhancing the data by combining features or performing some sort of applied statistics to it, if we were still unable to get any sort of sense out the data, we could go back to the source. But that's the sort of questions that I wanted to bring up, because in industry it's not easy. Data isn't in the format that we'd like. It's not like the beginner courses online where you just get a lovely data set which has loads of meaning. A lot of the time the data is poor, and it's up to the engineer to get it to a state where it can be used, and you spend a lot of time doing that, probably most of your time doing that, rather than the model building. But this data set is quite bad, so there's not much we could do with it. As I say, though, if we were needed to learn a product, if we needed to build a product that was going to test this water, the best way to do it would be to create artificial data. You know, the drinkable water would be, we would set the parameters of what drinkable water is according to the governing bodies around drinkable water, and we would also include data that wouldn't be drinkable, so our product could understand what the difference was. That would be probably my way of doing it. Researching the literature and creating data from that literature and training the model on that, because at the end of the day, if you're going to put this into production and people are going to use it to basically survive, it needs to be spot on. And if your data is not up for it and there's nothing you can do with data, you have to think about other options. Hopefully that makes sense.
Yep, thank you, that's helpful, thank you.
So this shouldn't be far off now. But as you can see, it's running up to 25, and it seems that it's getting, the new leader at the minute is the deep learning grid. So it's given us the flat metric of 67. So in the AutoML, it seems that this one is the best performer. It shouldn't be too long. So 500 seconds is probably about 8 minutes. So another 2 minutes we'll give it, and we should be fine. And we can take a look at the rest. But that's the thing as well with the AutoML. If the more models you ask it to produce, the longer you should put the time. 500 seconds is probably inadequate to actually get something meaningful, but 500 seconds just for the sake of this demonstration is more than enough. If it was in industry and I was doing these 25 models and I had quite a big data set, you could probably run this for 8 hours, if not more, to get the best out of it. Models like XGBoost as well do benefit with a longer training time. That is one to take away, because it uses, because a lot of the trees are parallel, it can just loop through the trees and pick up the weakest ones and see if we can push out more accuracy and whatnot. So the more training time you've got for XGBoost, the better. So yeah, but 500 seconds is more than enough at this point. So it should stop running in about 45 seconds. AutoML H20 also has an online platform as well. If you sign up to the Pro version or the subscription version, they have a GUI which is quite useful. And if you're aware of anything like Microsoft Azure, it's quite similar to that, where you can build a model visually and train it and whatnot. But the one I'm using is just the API. I don't have a Pro account, but the API is just as powerful, especially when you combine it with a Google Colab GPU. You can link them together and you get some good performance out of it. So this should be finishing in a moment. Nearly done. And what you'll see when it spits it out, there we go. It's got all the the metrics again. It's a bit slow. So this is the leaderboard. So the number one performing model was the deep learning grid one. And you can see its metrics there. We compared it to our previous metric, 67. And it's got, you know, other like the RMSE and the MSE as well. And then you can take a look at the metrics, the in-depth metrics of the best performing model. So it'll give you the full rundown to make it a bit more interpretable. You got, again, the F1 scores, the thresholds to them as well. The threshold values is quite an important metric in industry, and all this is included in the documentation that I have included. There is a large amount of information here, and I could be here all day trying to explain every single part, but you can see the ones we recognize, like precision and recall and whatnot. We can also use the best model on the test set. So we apply it to the test data, and it gives us a confusion matrix, and it gives us the metrics of how it performed on the test set as well. Again, it's very, very thorough. This one's quite interesting as well. So what we can do here is we run this one, and it saves the model. And as you can see, it's appeared in my runtime here. So it saved that model, and I can use that model. I can take that away and use it in another instance of the H2O. The only stipulation is that it has to be the same version of H2O. So you have to have the same installation. And we can overcome that by using things like Docker and Kubernetes as well. And that's what we would use in industry. But, you know, that's a great way. So you can train that model, and you can go to a colleague and say, I've trained the model. It performed this well. It performed better than yours. Take a look, and they can run it and check your results as well. And this is just the code to load it in. I'm not going to run it at the moment. And the next part is, oh, shouldn't have done that one. There we go. The explainability of the model. H2O is very powerful. So you get the leaderboard, and we can use the explain method, and we can explain it on the test set. So it will apply the model to the number one model to the test set, and it will explain its decisions. So we have the confusion matrix, we have the variable performance, so the feature importance. And as you can see, to make its decisions, pH was the number one importance, and so on and so forth. Variable importance heat map. So as you can see, the ones in red are the ones that were most important. And to what model they were most important to. So you can see all the different models here and what was important to each single model. That could be a good indication of hyperparameter tuning as well. Then we've got the model correlation, and how the models, you know, were similar in each other, and what, you know, what models use the same sort of information to make their predictions and whatnot. And then we have the SHAPS summary as well. And this is, you know, the case for the DRF1 AutoML. You can set this to take a look at whatever model you want, and it explains its decision-making process using the features. I have put a document linked further up to explain what, you know, how to interpret SHAP, and also the partial dependence plots as well. So it shows you the dependency of a particular feature. In this case, it's the pH over time and over what model, and how important it was to make a prediction. Again, I've got the documentation there to explain these charts in a lot more detail than we have time for now. But what I want to demonstrate is that the power of AutoML to produce all these instantly is very, very useful to a machine learning engineer. Oh, there we go, and there's the different interpretations and partial dependence interpretations as well. We can also take a look at certain rows as well, so we can explain row index 10. This is just looking at, you know, how row 10 was, you know, you can narrow it down that much and to see what sort of explainability, you know, the prediction for row 10, what was the thought process behind that for the model. And there we have it. It didn't really use the pH, but it used these ones to make its prediction. So it is quite interesting. It is quite powerful, which, you know, to get this sort of indication, it takes a lot of coding work, and you can do it with a click of a button with one line of code. So that why they are quite powerful. Just give me 1 second. And that is pretty much it. The further resources I've put at the bottom here, the machine learning A to Z templates and the data cleaning templates, I've put them together over time just to sort of explain how, you know, I've got a number of different templates that you can just plug your data in and see how it works, both the data cleaning and machine learning techniques as well. So we've got logistic regressions and classifiers and whatnot. So yeah, that is, I'm going to share this notebook with you, and hopefully you can use it as a template for future challenges. But yeah, that's it. Any questions at all?
So it was really good to see this kind of feature engineering and also explainability, which I think is a very important point in ML. So please, participants, do not hesitate. Please ask questions. Thank you again, Rich, for this nice presentation.
Not a problem. My pleasure.
Yeah.